Welcome to today's edition of tuition. Last time, in the last lesson, we ended up with the Cramer's rule, and we came to this point and said that the x values of any simultaneous equation in two variables, the x value is the right hand side. So this expression is the x value of the solution of the simultaneous equation, and this y expression is the y value of the solution of the simultaneous equation. Therefore, if the two lines are going to meet, then they will meet at this coordinate, which indicates that the coordinates of the point of intersection is equation micro and phi. Therefore, the point of intersection occurs at s equals to this expression, y equal to this expression. This is just a recap. Maybe as a point of interest, you can take your time and then copy this one to restart the whole thing again. Yeah. In our next section, we are going to consider a question that we couldn't finish last time. We'll consider it now at this time. So I would like you to take your time as I step aside to make the board more clear for you to see the board, so that we can take it from there. You can pause the video, freeze the video, and then you can have a proper view of everything on the board. Then you can copy everything, and then we'll come back again. Now we come back again. In the last edition of the tutorial, we solved the same simultaneous equation by, I think, 2 or 3 different approaches. I think we did them by elimination, substitution, and matrices approach. And because of the time constraint, the third method, which is the approach of matrices, we couldn't do that because of the time constraint, and we said that we'll pick it up in our next lesson, which is today. So the same simultaneous equation that we saw previous time, by the use of substitution and y equals to y approach, we are going to solve the same simultaneous equation by using matrices. At this time, if you see two linear simultaneous equations in two variables like this one, this equation that you see there absolutely is not different from this equation. It's not different from 7, 9, 5, 7, 9, 5, 7, x, y, multiplication. This is 3, 1. This equation can be expressed in this. In mechanics, you find such kind of analysis, they are very common in static mechanics. If you are doing mechanical engineering or electrical engineering or civil engineering, this equation that you see here is the same as this. Why? It is 7 times x, 7x, plus 9 times y, 9y. Then you come to the second, you come to this part. 5 times x plus 7 times y equal to 3 and y, 1. It's the same equation that you see there. So in this equation, this particular form, this one, we call it the matrix M. And this particular SY, whatever, we call it X. And this one, we call it C. So you can see that this equation can be expressed as this, which indicates that the expression here is M times X equals C. Very good. If you have M equals C, there is a primitive way, which is simpler way to bring the M to the right to the right hand side. It is simpler way. I don't want to go into more complicated way. It's the simpler way to bring M to here. You can find it out that X will be equal to M inverse C. Good. This is very important equation that we want to consider, and I'll call it equation. Let me call it equation alpha. Now, what is M? We are very much interested in so what is M inverse? The M inverse is the inverse of the matrix M. And we know that the matrix M is 5, but M, the matrix M is 7, 9, 5, 7. That's the matrix M. Good. And to find the inverse of M, which is this one, we say that let me do it section by section, so you shouldn't be carried away. So this time we have the next section. The inverse of M by definition M inverse of M is equals to 1 over determinant of M times adjoint of M. I'll call this one maybe this, yeah, I'll call this one equation alpha. Very good. Very good. Then what is the determinant of M? if you have a matrix like M, for any given, if you have a matrix M and you want to find the determinant of M, the determinant of M is given by, or sometimes it is denoted by this. If you see this one, it means determinant of M. And what is determinant of M? It's not a big deal. The determinant of M, you pick up the M. So the determinant of M will be 7 times 7, which is the determinant of M. This way, comes this way. 7 times 7 minus 9 times 5. So the determinant of M is 7 times 7 minus 9 times 5 for any 2 by 2 matrices like this one. This one is 2 by 2 matrices. And for 2 by 2 matrices, it is 7 times 7, or whatever is here times whatever is here, minus whatever is here times whatever is here. So 7 times 7 is 49, minus 9 times 5, 45. 49 minus 45 will have equals to 4, which means the determinant of M is equals to 4. I'll call this one equation. Now this one was equation. This one was equation alpha. This should be equation beta. I'll call this one equation gamma. So you can see that in the inverse matrix M, we have found the determinant of M. But what is the adjoint of M? The adjoint of M, by definition, is given by the adjoint. You pick up the M matrix and then you swap these two positions. So this green, whatever value it is, it comes down. And this yellow or pink or whatever value is there, it goes this way. So you swap their positions. In that case, the adjoint of M becomes we are going to swap the positions. 7 comes here. Whatever is here, you swap their positions. And the other 7 comes here. And we know that as soon as you swap the positions, these ones, you don't swap their positions. Their positions remain the same. They remain at where they are. They don't change. But once you have swapped this, this position, the 9, because it is positive, it will become negative. And the 5, because it is positive, then it will become negative. So you have swapped the position. So this one is called the adjutant matrix or the adjoint matrix. The adjoint matrix is when you have any 2 by 2 matrix like this. You swap these two positions relatively, and then once you swap their positions, you negate whatever is here and whatever is here, just as we have seen it there. So this one is called the adjoint matrix or the adjutant matrix. So you have this one. I'll call this one equation delta. Now that you can see that you have the inverse matrix, you have the determinant, which is 4, and you have the adjoint, which is this. So we are going to put equation delta and equation gamma back into equation beta. Okay. Before that, maybe I will have to wipe this one, but we are not going to forget the equation alpha, though I will need a board. But the equation alpha will be very, very important for us. So, take your time, copy everything up to this point, and then we'll pick up from this session. So take your time, copy everything up to this point, and then we'll pick it up. Now, welcome back. We ended at this point, and then we are going to carry it on here. So we say that X is equals to the inverse matrix, the inverse of the matrix M times C. What is the inverse of the matrix M? Now, the inverse of the matrix M is this equation. So we are going to put equation gamma and delta back into this equation. But I think relatively, because I need a board, this one I will bring it to, we will need it later on. So, put in equations gamma and delta into equation beta. We find M inverse of matrix M is equals to 1 over determinant, 1 over the determinant. The determinant is 4 times the adjoint of the matrix. Seven minus 5 minus 9, 7. So this is the inverse of the matrix. I'll call this one equation 5. Now, remember that, but from equation alpha, we had X equal inverse of the matrix M multiplied to C. Then we will take this portion, and then we will clean away this portion, and then we will put equation phi into equation alpha. Take your time, copy it, and then I'll clean this section as well. This is equation alpha though. So we are going to put equation phi. We are going to put equation phi inside equation alpha. So equation alpha now becomes X equal the inverse of matrix M. We see that it is the equation phi. So it is 1 over 4. And then we have here minus 9, and here we have 7, and here we have 7, and here we have minus 5. Then C, multiply to C. This one is multiplication sign, product sign, multiply to C. But what is C? C, we can see from this side, C is 3 1. So, what we are going to do is we are going to perform matrix algebra. So, because the space is not enough, take your time to copy from here up to here. Then I will wipe this session and we will perform the matrix multiplication algebra at this side. So at this time, take your time, copy everything from here to here, and I'll wipe this session and we'll pick it up from here at this point. This is where we left off. Now we are going to perform matrix multiplication on this equation. Here is by the way, this is big X. Big X. Good. And we said that the C was 3, 1. That was that. And the big X, which is this one, we find it out it is this one. So this one becomes X small and then Y equal 1 over 4. And then you have minus 9, 7, and you have 7 minus 5, and then a product of 3 and 1. Good. Good. If you have this equation, honestly, it's not different from X, Y, which is this one, equal 1 over 4, which is this one, and then you have here this one, you have 7, and you have minus 9, not necessarily minus 9, not necessarily 7 minus 9, no, it is minus in front of the 9, so 9, then you do it this way, 3, 1. Then you come here. You have should be neat. You come here, you have minus 5 and 9 and 7. Sorry. Then you have this one as well. Good. Then, yeah, very good. Now we are going to, the idea is that we are going to multiply this section to this one. So this is how we do it. You break them into pieces. 7 and 9, which is this one, is going to multiply to the whole thing. And then minus 5 and 7 is going to multiply to the whole thing. So this one becomes, okay, take your time to copy it, and then we'll wipe this section off and we'll pick it up from here. Take your time. Now, if we continue, we will have this one to be equal 1/4. Then 7 multiplied to 3 . 7 multiplied to 3, then minus 9 multiplied to 1. Then we have minus 5 multiplied to 3 plus minus 5 multiplies to 3, minus 5 multiplies to 3, minus 5 multiplied to 3, it has to be neat. It has to be order. You know, this should be an excellent work. 7 multiplied to 3, 7 multiplied to 3 plus minus 9 multiplied to 1. And we come here, minus 5 multiplied to 3 plus 7, which is green one, multiplied to 1. So we have, this one becomes the next one. The next one we have x, which is this one, y, good. And then we have equal 1/4, then 7 times 3 is 21. That is 7 times 3 plus minus 9 times 1 will be minus 9. Then we have here minus 5 times 3 is minus 15. Plus 7 times 1 is 7. Which is no different from x, y, I don't know whether you can see it properly. Maybe I have to make it smaller so that you can see it properly. X, y, equal 1/4 21 minus 9 minus 15 plus 7 Now, take your time to copy it, and then I'll wipe this session and we'll pick it up from this point. Take your time. So, we have x and y equal 1 over 4 minus 21, 21 minus 9 will give us 12. And then minus 15 plus 7 will give us minus 8. So we have x and y equal 1 over 12 times 1 over 4 times 12 and 1 over 4 times minus 8. Which implies this one is equals to 3 and this one is equals to minus 2. Which implies we have x, y, equal 3, 2. Which indicates that, which implies x is equals to 3 and y is equals to minus 2. Exactly what we had by solving this simultaneous equation by substitution approach, by y equal to y approach. This was the exact result that we have. So you can see that, this is also another plausible way of solving linear simultaneous equation like this form. You can use matrices. But as I told you previously, that to use matrices to solve equations like this, it's just like to crack a mere nut by the use of a sledgehammer. This is, very tough. This is very tough algebraic analysis. The algebra involving in this approach is very, very demanding. This is it. That's why I said to solve simultaneous equation in such a procedure or approach, it's just like cracking a mere nut by the use of a sledgehammer. But at some point, when you have 12 equations, you may wish to use this approach. This is it. So now, we come to the end of that session. Take your time to copy this one, and we will see what we can do. Take your time. Copy the whole thing. Now, welcome back. The next question that I would like us to consider is also a little bit tough. And it is going to require a little bit of time. So in that case, I would like us to conclude this section of the tutorial, and then in the next section, we'll pick it up from there by solving different questions. Different simultaneous equation by the use of elimination approach by the use of substitution approach and by the use of y equal to y approach and by the use of matrices approach. This matrix approach, sometimes we call it the approach of linear algebra. This is it. So I will see you again in our next tutorial when we take a different question. I mean, by using, I think, 4 approaches, as I've mentioned. Yeah, then I will see you again. And until then, I will say that the Lord Almighty God bless you, keep you, make his face shine upon you, lift up his countenance upon you, give you peace, and continue to bless you with wisdom and understanding. And may you stand out among your peers. I mean, as the psalmist said, my tongue is like a pen of a ready writer. This is it. May you be eloquent wherever you are, and may you be fruitful. God bless you. Bye.